Okay, so, well, thank you very much for the introduction. So actually, first thing I should say, I thought this was going to be an informal lecture for students. So I had to do some last minute changes, but hopefully it looks solid as a one piece. So,
oh, you're going to document it as a student, document it as a homework.
So actually, I mean, that's why I kind of made it more technical, because it was for students. So anyway, so we'll go from the opening to closing. And of course, I mean, I'm talking about model predictive control, so I'll repeat the introduction. So it's a few slides of the day before yesterday. And then, of course, we'll talk something new. So, how many of you actually attended the talk on Robust MBSE? I apologize for repeating the introduction on MBSE, but I can't give you two different introductions on the same topic. It wouldn't be consistent. So, to start with, actually, this talk is it's really based on a framework which is actually partly developed, but essentially it's developed, but it's partly in the process of publishing, and it's a collaborative work with Bill Levine and Bežet Ačikmeze. Bežet is my host at UT Austin, and you should know Professor Levine, so he's here with us. So there are a few papers, I mean, the references are. So the first time we presented this was at the Vienna workshop on optimal control and economic gains in an invited session. Then we have a conference contribution to ACC, and then CDC and journal versions coming being finalized. Day from yesterday. So how to explain MPC? And once again, I'm really sorry for being repetitive to some of the people who attended. So really what we're talking about, I think this analogy is a more general analogy, because essentially, if you think about cognitive psychology, and Jean Piaget is one of the really founding fathers of this field, what you really look at, you look at the case of the baby and how the baby learns about the environment and how it actually learns to control the environment. And what you really figure out, the first thing the baby needs to do, it needs to build an image of reality in which it lives. And then, of course, once it builds the image of reality, it figures out what it wants to attain, which is the aim, and then it takes an action. Taking an action, of course, it's done with the goal to achieve certain aim, and then, of course, it compares what's happening in the process. And if you think about this, of course, almost all of us have been in the position of the baby, and a few of us have been in the position of the guy who is holding the baby. So the baby is my son, and the guy who is holding the baby is me. Just see my hands. So, but essentially what this has to do with the predictive control, well, actually, when I was in France in 2014, I spent some time and talked to a person who was one of the first, one of the early contributors to predictive control, Jacques Michelet, and we came to this comparison. So essentially, if you think about the image, that's what we in control call model. If you think about the aim, that's what we call reference. If you think about the action baby takes, that's what the control is about. And if you think about correlation, that's a feedback. So really what happens, baby is in a bed, it's very unhappy because it's like to be taken up. So it has to take an action to change its position from the bed to close to the ceiling, and then of course the action is crying. And being a rational and reasonable parent, you act. You take a baby and you do what baby likes. And suddenly you see a smile on their face. So that's your reward. It's also a reward for a baby at the same time. So now, if you think about the paradigm, what is really happening here is, we are talking about interaction of a system and basic decision-making process. You know, from the system you're getting certain information, which typically the state feedback setting controls the state. This information is fed through the decision-making process, and essentially you're figuring out what to do, meaning you're getting the control. Now, where predictive control matters, it matters a lot when you have constraints and you want to satisfy these constraints, when you want to stabilize the system and you want to optimize performance. And what is really model predictive control? Based on this diagram, it's essentially just a repetitive decision-making process, where the basic decision-making process is finite horizon optimal control. So you're solving finite horizon optimal control problem. At a given state, you're applying the first control and you're repeating the process. And these go on along the actual control process which realizes in reality. So now what does that mean? Essentially for an integer n, which is called prediction horizon, and at a given state x, which is state admissible, what you would like to do, you'd like to select predicted sequences of control actions and control states over horizon length n, which are dynamically persistent. Your f represents your model. are admissible with respect to the constraints, and, okay, so these highlighted parts are terminal constraint set and terminal cost function, and they're actually the key themes of today's talk. Now, for that reason, I'll just essentially avoid describing this picture. It will come up a few other times as we go along. So what really happens here is the ingredients actually assure that this process is consistently improving and stabilizing under really mild assumptions. Now, what is your control? The control is essentially just the first term in the optimal sequence, and this is a feedback which is implicitly evaluated at the current state. The reason why it's a feedback, it is because essentially you're repeating the process. So as you get the state, you solve the optimal control, you get a new. So at different states, you're getting different controls. So that's why it is feedback. However, what is important, your predictions and optimized predictions are open loop. So at the given state X, forward in the process, you're doing open loop predictions. And it is the repetition that actually accounts for the mismatch of the actual states and the predicted states. That's where you gain the feedback. Okay, so in principle, what we formulated here, what we described here is nothing else than a mathematical programming problem. In general, it's a nonlinear. Of course, it depends very much on the properties of the function f and the constraint set sets, as well as on the stage and terminal cost functions. In many frequent cases, f is a linear function and constraints are linear inequalities, and cost functions are quadratic. In this case, it's actually end up in a kind of stupid convex problem, and in fact, even quadratic. So, ultimately, what is happening, how do you implement this? You can do it in a few ways. The traditional way is actually to solve online this basic decision-making process. So you solve online optimization, you select the first term in the optimizing sequence, you apply, and you repeat the process. However, because this is a mathematical programming problem, you can actually look at the theory of parametric optimization, and you can find the functions which actually solve certain optimization problems. And this gives you something which is known as an offline solution. Once you have an offline solution, you find the functions of the state X which optimize the cost, and then essentially online you implement this by evaluating the functions, which in many cases reduce to the online lookup tables. Now, of course, you can combine the two if you want to get some efficiency. Okay? True for trade-offs. But this is not point. So now, new things hopefully. So as I said, let's just sum up the key facts. So we have a dynamics which represent the model. That's x plus equals f of xu. F is the state transition map, x in your states and controls. We have a constraints. These constraints model whatever you want to treat to the whatever. I mean, these constraints could be physical constraints. They could be constraints related to the safety considerations. They could be constraints related to the law regulations of the system, and what you have. So essentially, you model this. Now, what you really want to do, you're looking at the cost, which is the sum, accumulated sum of the stage costs, and essentially that's measured to the function stage cost function L. The tool is, as I said, model predictive control. It's a repetitive decision-making process. Now, okay, so there is no any more finite horizon. It's optimal control. Now, the reason for this is essentially what you would like to do ideally is you would like to solve infinite horizon optimal control. Now, typically solving infinite horizon optimal control is not so simple, excluding some very well-known, important but very special instances, such as linear quadratic regulated instances. In general, with the constraints, getting the infinite horizon value function is not so easy. And furthermore, if you look at this, you're really looking at a kind of either finding certain fixed functional fixed point, or actually looking at infinite dimensional optimization. But the whole point of infinite horizon is, once you actually generate the infinite horizon control process, in the perfect world, you can actually slide along the infinite horizon process. So there is no way to improve. So if you computed infinite horizon optimal control at a given time x, you can just shift along this trajectory. That's optimal forever. So that's a huge advantage of infinite horizon. In the perfect world. Perfect world means there is no external entities. The dynamics are perfectly matched to the reality and so on and so forth. Of course, perfect world hardly ever exists. So what happens in the actual case, actually you have to modify it. And this is what they said, those two ingredients are key ingredients. So how do you actually modify infinite horizon? So what are two obvious ideas to do? Anyway, two obvious ideas. What would you do? If I tell you I don't want to do infinite horizon, I would like to do finite horizon. What's the first thing that comes to mind? You just trunk it. Okay? So first thing is what you say, let me don't worry about infinite horizon, let me actually kill off all these terms after that, and I have some obstacles, I want to avoid these obstacles. So well, I mean, what I can do, I can start making, I can try to solve very hard non-convex problem of going from y to f. But on the other hand, I can actually do local convexifications of this problem and say, okay, let me go from y to b and a, from b and a go to c and b, and from c and b go to f. Now, if I've done this, I have essentially introduced intermediate terminal sets. So I'm going from y to b and a. From there, I know I can go to c and b, and from there, I know I can go to f. So actually, it seems to make sense. Of course, I mean, again, you can do many other things. You can hit obstacles if you're not careful, but you don't want to do that. So what I'm trying to say, the way to build these terminal constraint sets, you need to use reachability, backward reachability in particular. And that's relatively easily doable. Now, but you can use this paradigm of general predictive control to actually easily construct the paths in a very complicated scenarios, which lead to non-convex optimization and non-convex optimal control problems, which are quite complicated. So, just to summarize, this is a brief lecture, I'm really sorry. So, it's obvious that by allowing more freedom in choosing your terminal conditions, you improve all properties. I mean, if you do it smartly, you don't want to replicate the same set over and over. In that case, you don't gain anything. But
actually, go back one slide.
Sure.
Now, suppose, just hypothetically, that a much better choice than B would be to go on the outside.
Well, so this is only used, of course, I mean, once you build the, okay, so essentially building the cover is not necessarily unique, so you may have multiple covers.
You may also produce an inferior result.
Of course. So essentially, the other option would be to go this way, but I mean, it would be quite complicated for me to explain it in one slide. So essentially what one does, really, you build as many terminal sets as you can, and you consider them as intermediate terminal sets, and then you work out. In fact, actually, with a bit of effort, you can build a tree based on your trajectories, and you look at all the trees, and then do optimal control with the search of the trees. You know?
But the point is, of course, that you need to do this in order to be able to solve the problem. But that anything that doesn't take the whole problem, the restrictions that are extremely valuable like complexifying the problem, also do quite possibly give up the best solution. It's that you're doing this trade-off between computability and true optimality, which is fun. I mean, it's just one wants to understand that's what you're doing.
I mean, if you were really to, so I begin with the so because there is uncountable many covers. Actually, it's a power set, if you want to go mathematically. So it's a family of sets, and this is what it's a power set really. But you can restrict it to finite things, and if you restrict it to finite things, you can build the chains out, these micro chains, so you can do so many things very easily. But the idea is this way, I mean, instead of, and I think in robotics people did use this, what they call waypoints. All what I'm trying to say, actually, these terminal sets were using their generalizations.
We do this actually in the undergraduate control side without telling you. Well, in the inverted pendulum experiment, we break into two parts. One is to get the thing vertical, close to vertical, and the other is stabilizing the inverted position. So it's exactly what you're doing.
I mean, this is the only way, so actually, here is something actually I couldn't put in real-time smart autonomous behavior. I mean, if it's not about real time, we can do much better, much more sophisticated thing. But if you want to compute something fast and rapid, this is really a very nice way to go forward. So, in any case, so, of course, I mean, you have to increase certain level of complexity, but as Bill said, there is a trade-off. The trade-off is how many of these covers you employ, how do you construct them. And one of the things that actually in the standard setting, what I wanted to say, the dynamics of terminal constraint sets and cost functions are not necessarily stabilized. You may stabilize the control process, but you may have multiple terminal sets and terminal cost functions which work at the equilibrium. So your I at the equilibrium might be multi-value. Anyways, that can be stabilized by just introducing some nominal equilibrium terminal triplet. That will be in the papers. It actually draws attention to something else. Now, closing, I want once again to reiterate my picture on what really matters in predictive control. For those of you who are here, again, apologies. So, it's all about integrating things. Okay. So you have to, if you want to make some progress, you have to integrate disciplines. You have to integrate estimation and control. You have to integrate identification and control, and so on and so forth. In other words, you really have to integrate MPC's components in the utilization. That's all for today. And this was really a step towards making MPC an integral part of autonomous systems. And again, a lot of days. Double night session, workshop, they will be much more detailed, very dedicated to special things. And the session is really nice. There are quite a few very good people involved. So they're all at ACC 2006. We'll be advertising via emails things very soon. So stay tuned, so to speak.
You might mention that the ACC this year is in Boston, and it's
Yeah, but-
right around July 1st.
So I think, well, I mean, it was lecture.
It's
So
okay, it's okay.
That's all.
So,
I don't have much more to say.
Thank you. As he says, questions are welcome. And look, I mean, John over here interviewed 30 questions, so it's up to each of you to produce 2 questions. Go ahead.
I have a question,
Sure.
but I still don't remember your keywords and stuff, so I hope you help me. In your examples, okay, so basically this is like a sequential decision process.
That's
okay?
right.
And you get examples for visiting a friend, which is a spatial example. So you have different parts of space, and then it becomes pretty clear. You go from here to there, you go from here to there, etc. You set smaller goals and so on. Okay? And how did you call those? You had a name for those variables.
So ranch, city, street, house.
Yeah, but in general, you call them how?
They're not-
They're intermediate goals, actually.
So they're intermediate terminal constraints.
Right. So now imagine, okay, that you have to assemble something, okay? Some little machine, something. And there's many ways of doing this. Can you describe how would you think that you would produce this, how do you call them? The constraints,
Terminal constraint sets.
you know, the intermediate things.
Well,
Does my question make sense?
yeah, absolutely.
Of course.
In assembly, though, the decomposition, I think, is relatively implicit in the problem. So if you know the sequence in which the parts need to be assembled, then this goes immediately into action. Because
But if you don't, yeah,
But
I understand that. If you have a
If
recipe,
you're assembling something, you should know the sequence.
well,
of
no,
what
no,
you're doing.
but you don't necessarily know the best sequence. That was the point of my question. That if you don't know what sequence in which to assemble it, then the problem becomes much more complicated. Because what you could do is, at least in principle, you could try different decompositions and search for the best one.
right.
So I mean, if you know at least one decomposition, if you know at least one sequence, you can apply this. Now, you may have multiple sequences, or you may not know sequences. They may, I mean, assembling may become known upon certain task, so to speak. Something happens, configuration changes. Of course, in these situations, you need to generalize this. I mean, you need to provide more information.
But if you have that recipe, so to speak, that plan,
Sequence of
then you can directly apply this.
Yes, I think it's applicable.
Right.
I think the reason why I got this example of visiting a friend, I was trying to find a very simple example which is intuitive, which is something that everybody does, and which fits what actually
Right.
appears to be overlooked in the field. I mean, it's a little surprising because even though we do want to make predictions over a long horizon, we never really predict things over a long horizon. What we're really doing, we are doing really partial predictions. We are predicting over a short horizon, and we are making sure that these short horizon predictions are consistent. So, let's say, for example, this is how I do it. I want to go on a holiday. So I find a place where I want to go, I figure out the prices, I book something. Then, at the next point in time, I figure out what I'm going to do during my holiday. I mean, I can't do everything at a single instant. I don't know, I need more information. So essentially, it does make sense to break the long-term predictions into sequencing of short-term predictions. But the key point here is to ensure dynamical consistency. So to ensure that actually you can recover at least approximation of this long.
But that's a fancy way of saying that the intermediate goals are achievable.
Yeah, okay.
And this is a standard thing in robotics anyway, right? In moving a robot from A to B,
That's
You
right.
know, you move it not, you don't generate the trajectory as one big thing. You go, well, I'm going to go from here to here, and then from here to here. And in fact, often enough, you actually want to stop at the intermediate points.
No, it's fascinating, okay? So, for example, even, let's forget the friend and all, you want to pick up something. So this is the right thing to do, because that something could be moving, you know, somebody may be taking it. And all the algorithms that are out there today in the community, when they want to pick up something, they just find where it is, and then, you know,
It becomes very complicated to actually work out the maneuver. In fact, actually, we did it for the other reasons, but as we started writing things, we started figuring out that actually it naturally fits in so many scenarios, and the reason why it fits, it's essentially almost natural way to do things, so to speak. That's why actually it seems to have kind of this multifaceted
well,
application.
I mean, not only that, but the advantage that I also see, being a sequential decision process, before you act again, you can think. And you don't have to just do the optimization that you are doing, you can do many other things. So this cycle of the sequential decision process makes perfect sense for a system that also has to perceive the environment.
Actually, I'll tell you something very interesting.
Because one thing you are not describing, and I don't know how that would affect the overall theory, but you are not describing the part of the system that perceives the environment. You are assuming some things that are given. But you, in the general case, anything you figure out about the environment is something that you are perceiving.
So there is a coupling of learning and control.
Exactly.
So, okay, I mean, this is now assuming one of the two is fixed. You need to perturb the other direction. So, of course, I mean, adding, and that's what I was saying, the right way now to do things is to go towards integration, to integrate learning, to integrate perceiving, sensing, whatever you want to call it. But I don't still see a problem of this paradigm, because paradigm, what really changes is how do you define this basic cycle. Everything else seems to work. You know, like still, by repeating the thing you gain a lot.
Right.
Sasha and I had a little discussion about other analogies. I don't particularly love the baby analogy.
This one is better.
But I do love the chess analogy. So in chess, you plan ahead. You do exactly model prediction, right? Before you move, you try to extrapolate out as far as you can all of the moves that you and your opponent would make. You make one move, and then the opponent makes a move. If that move is different, no matter what, you now rethink the problem. Because if that move isn't what you expected, you have to change everything. And that's a piece of model predictive control that Sasha's done a lot of work on and hasn't talked about here, which is that sometimes the problem has significant stochastic component or unpredictable component. Unpredictable, not stochastic, in that the model is not exactly right, things like that. And so model predictive control was chess, captures a great deal of that. It also captures the impossibility of solving the problem all the way out to infinity. And so in order to make it tractable, you have to find what they do in the computer is they find heuristics that are helpful. But you could do something else, which is to emphasize tactics more and say, okay, my goal in the first 10 moves is to get up one piece. And if that's the goal, that's probably going to be sufficient to win the game. And so it's a very sensible intermediate target. And that's what this is about.
Yeah. So I mean, it's a bit surprising, but in fact, this description is much better for what's been done. And it's a bit surprising if you look at it. It hasn't been observed earlier in predictive control.
That's what I'm wondering. How come? I mean, because this concept is like an obvious one, like the big ones.
Obvious things become obvious once they're done. That's kind of trouble with many things. So the way I came to it from a completely different problem. I mean, first, there is a lot of interactions I had with built in predictive control, but I worked on a problem which is completely unrelated. It was a problem with set invariance under output feedback. How to define notions of invariance under output feedback. And it turned out you need to employ certain families of information sets. And I've done this with Einstein from Israel. So anyways, you figure out that actually what really happens, you have dynamics of these covers. And then actually the moment what you really realize, but when you observe the output, what really happens, you have one of these trajectories, one of these sets. And then I realized, look, this is immediately useful for predictive control, just an intermediate target through which you traverse your system. That's how I came to it. But I think essentially it is a bit surprising that it hasn't been observed in predictive control already.
I think
It is a bit surprising.
Well, but sometimes that's just the psychological bias, what the psychologists call set, right? This also, so historically what happened is that people developed optimal control theory. And optimal control theory is open loop. And there are a few special problems like this linear quadratic Gaussian problem for which the theory gives you a closed loop control. And that's really practical, whereas the open loop controls are not. So in the process industry, the linear quadratic problem almost worked, but they didn't understand the dynamics very well, and they had saturation. You know, the actuators would saturate, so they're not linear. And so they thought about ways in which to use the optimal control theory to get closed loop controls that dealt with saturation. And that's really where model predictive control started. I think there has been always this bias towards you start with an optimal control problem. And that's an open loop problem. And now what we want to do is to replace that, is to approximate that by closed loop control that is nearly optimal. And doing that, the next step is, okay, well, it's not optimal. And if you think about the mathematics, you don't even know if it's stable, you know, which is very bad. So the focus of theoretical attention was on proving that this closed loop control was close to optimal and that it was stable. And the practical guys don't care so much about either, right? They want it, because another view of this is, we know as control engineers pretty much how to design single input, single output control systems. Sometimes you can't do it because they're too hard, but you more or less know how to do that. This is the only tool we have for multiple input, multiple output systems. And also, you think about software decomposition, I mentioned in the undergraduate controls lab, we do an experiment in 2 steps. The problem is, you know, it's just basically a very classical experiment these days. You have a cart and a pendulum. So normally the stable position for the pendulum is down, but if you move the cart back and forth, you can swing the pendulum back and forth, and you get it close to vertical. Once it's close to vertical, you can stabilize it there by a linear control. So I have a 2-mode controller, exactly. So I have a built-in, an intermediate target, right? So I start here, and I want to get into a window that's about this wide at the top. And I can do that optimally. I can, you know, and using model predictive control as a way to get to there. Once we're there, you know, then I have, you know, again, an optimal control problem. This one is easy because it's linear, and so I don't even have to solve the problem. In general, that's the case where we get a closed loop control from the open loop optimization. But as you say, it is pretty natural, and it is a little surprising that people didn't figure it out before. But, you know, there are a lot of very obvious things that people don't figure out. It's just
Exactly.
So the students owe us about 28 questions.
Actually, another 10 minutes. So
Yeah, well,
another 42 questions.
Well, no, the problem
And my
is,
answer is 42, whatever you ask.
the problem is if you wait another 10 minutes, John will be here, and then we'll be here until 12:30. Of course, we'll learn a lot in a half hour.
Oh, well, thanks very much. It's really good what you mentioned of actually interfering, essentially trying to make interaction of perceiving and controlling. I think it's quite natural next step.
Do you have any software that you have developed with regard to this?
I have a lot of software, which are in the form of a personal toolbox, which means I can do a lot of things, but if I let somebody else to do, they'll be lost. So the moment I get a position, I get a student, one student will be just making this available properly for everyone. So a lot of software for this and some other stuff. It just essentially, you know, over the time you develop quite a few routines, you start building toolbox, and then you face this decision, if you're not really properly stable, so to speak, if you release toolbox, you'll get more problems than actual benefits.
Okay.
Because everybody's going to write to you to, so you need to kind of be stable before you release the tool. So,
There is a subclass of MVC for which there are, I think, tools available, tools available. That subclass is linear dynamics, convex performance measure, and convex constraint cells. Because then the problem reduces to a convex optimization problem, and those have, snap your fingers and there's the answer. It's guaranteed to be the answer and to be unique. So for those problems,
Right.
so for this one, there is a lot of, I mentioned compression tools, there's a lot of other toolboxes which kind of might be used, might be tailored.
You know, in the art laboratory, I don't know if you visited the art
I
lab.
would be quite happy to visit.
Have you taken into? Well, one of the problems that we're looking at is open and close to ground the meaning of those verbs.
Okay.
So to be able to open things like cabinets, a door, a window, and close them. And it seems to me this is the only way to do it.
Thank you.
Because when you perform an action, this, if you have some perceptual capabilities, this gives you the ability to, keep this continuous right, because you have to see what you're doing. You have to be measuring the effect of your action.
Absolutely. I agree.
And it seems to me there is no other way of performing that. So we will try to see whether we can develop implementations that are based on this.
Well, I'm here this week. I guess I'll have some time to, if you want me to visit or to see, I would be delighted to do that.
Very good. Thank you, it was a great talk.
Thanks very much.
let's thank you all.